Hello everybody, I'm Jaya Srivalsan Nair. Today I'll be presenting a paper RoSELS Road Surface Extraction for 3D Automotive LiDAR Point Cloud Sequence. Dwayne Katkoria is the first author and my co-author. This work has been done at the Graphics Visualization Computing Lab at the International Institute of Information Technology, Bangalore, IIITB in short form in India. Let's first understand what 3D automotive LiDAR point cloud sequences are. LiDAR technology is where light beams are emitted from the sensor and the time it takes to return to a receiver, which is part of the sensor, indicates the distance the beam has traveled until it was incident on an object, which is an obstacle on its path. When the sensor is mounted on a moving vehicle and captures 360 degrees rotation, we get the automotive LiDAR point clouds with three-dimensional location of the objects in the scene, which are around the ego vehicle. A single 360 degree scan gives a single point cloud. Given it's a moving vehicle, several point clouds are gathered as the vehicle moves along its entire trajectory. We refer to these point clouds as a sequence, and they together provide information of the entire trajectory. The general data analysis that is implemented on automotive LiDAR point clouds include semantic segmentation, which is where points in the point clouds are labeled by an object type such as car, truck, pedestrian, building, etc. And then we have something called the semantic understanding of a scene, where one predicts if the voxel in the point cloud space will be occupied in the future and what type of point will be occupying them. We then have 3D object detection, where we try to detect 3D bounding boxes around objects in the scene. Finally, we have our novel analysis, which is in geometrically extracting the navigable surface based on the retrospective information of the sequence traveled by the ego vehicle. This work would be a predecessor for anything that wants to predict the surface that an autonomous vehicle would be traversing or estimate such a surface for future operations. Unlike the other two analyses, which can be directly done by learning from previous instances on a model, in this particular one, we require a workflow. We focus on the road surface as a navigable space of the ego vehicle. Our proposed algorithm is for the stated problem is RoSELS, that is the road surface extraction from LiDAR point cloud sequence. It has these 5 major steps that you see on the right. Our novel contributions are: number one, designing and automating an end-to-end system for road surface extraction. Number two, one of the steps in this workflow is the frame classification, which uses projection of the point cloud to an image, and then we run it for finding the road geometry that is captured in the top view. Number three, we finally demonstrate a novel use case of using surface methods, surface generation, and geometric methods for an application such as automotive LiDAR point clouds. Now, this is the entire workflow of RoSELS. We'll explain each step in detail now. So, as we mentioned earlier, there are 5 main steps to our workflow for the implementation of RoSELS. So, S1 is for the ground point detection. S2 involves 2 parallel steps which can be done independent of each other. S2A is what we call the road edge point detection. S2B is the frame classification. S3 is the third step, which is the edge point set smoothing, and S4 is the 3D surface extraction. The inputs to our system are the sequence of the input point clouds that we see here on the left. And we then finally have the sequence trajectory, which encodes the poses of the vehicle, the rotations of the vehicle, and the actual location of the vehicle along the trajectory in a global coordinate system. Now, our system also adds complexity as it progresses. So we first start with operations which are done on points, then we progress on to doing operations on the frame, and then finally on the sequence. So for ground point detection, the literature survey shows that height-based features, even if they are handcrafted ones, in a supervised learning model perform very well. Hence, we pick the height and position based features used typically with airborne LiDAR point clouds. For local features, what we mean is that we determine a local neighborhood using k nearest neighbor with an additional constraint of a radius for a spherical neighborhood. We use the local neighborhood to compute statistical descriptors such as mean, standard deviation, etc. For local features, we also use different spatial resolutions, such as different K values, thus giving us multi-scale features. This is because multi-scale local features are known to perform very well for classification. In a similar fashion, we compute the global features, which are computed with respect to the statistical measures computed for the entire point cloud. We first remove outliers in S1, that is a ground point detection. Now, for outlier removal, we use a widely used method called the iterative closest point ICP registration. The idea here is we use the temporal locality to check the persistence of a point across consecutive time frames and retain them only for further analysis only if they persist. So here we check if the registration is done for the in the x minus 1 frame, that's the previous frame, and the x frame. Thus, we use information from three frames, that's x minus 2, x minus 1, and x to check the persistence of a point sample. Once we remove the outliers, we are now ready to implement S1, that is the ground point detection using random forest classifier. So what we do here is we run the random forest classifier on the multi-scale local features and the global features that we talked about earlier. And we then find, we label the points as either ground points or non-ground points. We need to now identify the extent or width of the road. Hence, we compute the road edge points. This is done by taking the ground points from S1 and further classifying them using a Gaussian mixture model, thus we getting flat and non-flat regions. Here we exploit the application of height differentiation, which is already used a lot for edge detection in images. Thus, we use features of height difference in local neighborhoods as well as something called the 2D accumulation map in the Gaussian mixture model. 2D accumulation map is nothing but the square neighborhood centered around a point where we compute the neighborhood on the projection of the point cloud on the XY plane. Now we have completed S1, so let's move on to S2. So for moving to S2, we pass the ground points and the non-flat regions to the frame-wise operations. Now, when we use the non-flat regions, we assume that they form the curve of the road or the banks of the road. Now, of the ground points, we generate a top view image first, which will be used for S2B, and then we also generate the range view image. Now, S2 So the top view image is a projection on the XY plane, and the range view image uses the spherical coordinates, that is the theta phi projection. S2A is used for determining the road edge points. We need these points to generate approximate surfaces. Depending on how we use or not use the internal points for generating the surfaces, the boundary points of the surface have to be sufficiently sampled. At this juncture, we already have the curve points, but we need to find the optimal curve points or the significant curve points which define the banks of the road. These points are thus the closest to the medial axis of the road, or or in simple terms, the center line of the road. Thus, we take range image. In the range image, we walk along each row, and whichever points are the closest to the center line, the curve points which are closest to the center line are retained, the others are thrown away. Now we do this for the right bank and the left bank of the road, and we do it for front of the vehicle as well as back of the vehicle. Let's now take a look at the frame classification, which defines the road geometry in the S2B step. Now, when we look at the top view projection of the point cloud, the human eye can perceptually detect if the geometry is that of a straight road or of a turning or of a crossroad. Hence, we use this rationale for classifying top view images. We take the ground points from S1 and render them using a sequential color map, that is a gradient color map, which represents the remission values in the ground points. We now use transfer learning using ResNet 50 architecture for frame classification. We have specifically chosen this architecture because recently it has been successfully used for accurately classifying scenes which have perceptual distinguishable features. Here we use a hierarchical classification where the first level is a straight road and the curved road, and curved road is again subclassified in the second level of classification to crossroads and turning. In this work, we focus only on straight roads for three reasons. Number one, curved roads need more boundary points samples for reconstructing them piecewise linearly. Number two, we need a view which is more expanded from that of the ego vehicle to capture the larger road topology. Number three, we need more internal points in the case of curved roads to generate the surfaces more accurately. We now reach the last step set of the sequence wise operations. Here we need additional information of the ego vehicle in a global coordinate system provided by the entire trajectory or the sequence of the point clouds. Now all the road edge points are converted to global coordinate system, which all takes into account the position of the vehicle as well as its pose so that we get accurate edge points. Now we run an algorithm called RANSAC, that's the random sample consensus, which is used for line detection. This is done to remove the noise in the edge point set so that we get a sleeker, cleaner set of edges. Now this is step S3 in RoSELS. Now if you look at this image, we can see that there are lots of edge points that are detected here along the right and the left bank of the road. And when we run RANSAC and we looked at the zoomed image, we see a cleaner set of edge points. Now we are in the final step S4 in RoSELS. We extract the 3D road surface using Delaunay tetrahedralization of the filtered edge points. Here we have not used any other interior points as we are focusing only on the straight roads. From the tetrahedra that we extract, we now take the topmost triangular surface as the road surface, thus constructing the surface itself. So now let's just take run some experiments on the data set in semantic kitty. Uh, and we look at the training sequences of only the straight roads here. So we see that for straight road trajectories in the training sequences, our method performs relatively well. In A, that's the top row, we see how edge points are extracted at the end of S3. In row B, and also in the zoomed version, we see the extracted surfaces at the end of S4. Now, in the absence of ground truth for surface evaluation, We use the ground points from the ground truth of the semantic classification of semanticity in RoSELS, that is to skip the ground point detection, and we extract the road surface in this roads in row C uh, completely using RoSELS, and then we compare the two results in B and C by overlaying them. So what you see in row D is an overlay of the mesh from B and the wireframe from C, and we also, so we visualize it and we see that the results are fairly similar. And at the same time, we also quantify the results to see the RMSE score, that is the root mean square error. And we see that they are all around they are under zero point 0.5 meters. Now, to give a relative sense, the data set is such that for every frame, we have an extent of 51.2 meters in front of the vehicle and 25.6 meters behind the vehicle. So in that regard, the RMSE scores are fairly low, are negligible. Now let's now take a look at how uh, take a look at the results of how the RoSELS algorithm works for all of the for the training sequences. Sorry. So here we see that a lot of for all the training sequences, the percentage of the road points preserved as ground points does not reduce after the outlier removal in S1, which is what we see here. Like they are very similar percentages. So this shows the efficiency of our outlier removal process while preserving the road points. Now let's take a look at how RoSELS fares for other sequences. Right? So we see how for a testing sequence for which we don't have the ground truth, RoSELS performs very well and we get a visually uh, accurate, approximate um, road surface. Now, when we look at the training sequence here, we see that this is a curved road, and we see that the medial skeleton or the center line of the road itself is not extracted completely using RoSELS, which leads to a very sparse extraction of the road surface as well. Now let's also look at a few more significant results of our work. So we have found that multi-scale feature extraction has led to better accuracy in the ground point detection. And we also see that after we do the outlier removal using ICP, we get far better scores for classification. Then when we look at the classification for the frames, we see that for the straight and curved road at the first level of classification hierarchy, we see better classification accuracy than having to do both levels of classification hierarchy, that is straight road, turning and crossroad. This possibly can be explained by the lack of the number of samples that we have for training for the crossroads and the turning. Now, this is the final result that we have. Here we see that a large proportion of the points which are marked as the edge points after S3, after we do the road edge point detection, most of them are from the road class type or the sidewalk class type. Now, what this indicates is that these are the classes which were manually annotated in the original semantic kitty data set, and hence we see that RoSELS accurately identifies the curve points from the classes it's intended to be in. So with this, we'd like to conclude our talk. Overall, we would like to say that our system RoSELS efficiently extracts road surfaces from a sequence of LiDAR point clouds. It has been currently implemented only for contiguous straight roads, and our goal is to extend it for curved roads, which is in the scope of the future work. At this point, we would like to acknowledge the kind support of the MINRO grant from the government of Karnataka. Uh, it's a state in India. And we have also benefited a lot from the discussions with our collaborators at Ignitarium. So thank you for your attention. We'll be happy to take questions at this juncture.